My first live stream in a while. I've been off the air for a couple of weeks, but now I'm back. And actually, this is the first live stream I'm doing for my Discrete Structures course this semester. And this is going to be kind of a review of what we talked about last week. So if you missed the classes last week, we talked about hashing and checksums. And I'm kind of going to do if you will, excuse the pun, a rehash of what I did over the 2 days that we had class last week. So in short, as I have mentioned, hashing is kind of like, well, the idea is to take a message of some sort. It could be a small amount of data or a large amount of data, and distill it down to a fixed size output value. So this is an algorithm that crunches up, takes a whole bunch of data, grinds it down, and then produces a fairly small output value. And by small, I may mean 128 bits, 256 bits, 1000 bits, somewhere in that range. So for like a 128-bit value, that is, I believe, 16 bytes. So it's actually not that big. And so I use the analogy of a coffee grinder for hashing. The idea is actually I've got a real coffee grinder here, right here. And so the idea is you pour in your data. Now I looked through my kitchen this evening, and it turns out I don't actually have any coffee beans. So I'm going to have to use a substitute for that. I have cereal. So you take your coffee grinder, pour in some data, turn it on, so grind it all up. Excuse me, it's probably going to be kind of loud. Okay, the bits have all been ground up now, and then some dust has flown around, so I've got dust on my computer here. And then you open it up, and then you take a teaspoon and you just reach into there and you pull out a little bit of data. And this is your hash value right here, what I've got in the spoon. That's your hash value. Okay, so out of all the data that I poured in, I took out only a little bit of it after it's been all ground up. And so the idea is I've kind of got a magical coffee grinder there. If I pour in the exact same data again, everything is exactly the same down to the molecule. So every single coffee bean is arranged exactly the same way, they're exactly the same size, and I grind that thing up again, I will get, and I dip my spoon in there again, I will get the exact same little spoonful of that data the second time. So every time I pour in the same data, the exact same data, I will get the exact same output out. But if anything is out of place, one of those coffee beans is a little bit rotated, one of them's missing, two of them is in swap positions, one of them's a little bit bigger, a little bit smaller than they were before, then I will dip my spoon in and I will get a different set of data, a different value coming out. And in fact, the way the hashing algorithms work, it's completely different. It bears no resemblance at all to the one I got originally. Okay, so that's the idea behind a hashing algorithm. And let me talk to you about some common ones. So these are common hashing algorithms. And they go by abbreviated names like MD5, SHA-256, SHA-512, RIPE MD160. And those numbers following them, like the 256 and 512, have to do with the number of bits that these things output. For example, MD5 outputs 128 bits. SHA-256, you can probably guess, outputs 256 bits. This one outputs 512 bits. And this one outputs 160 bits. So these algorithms are essentially different coffee grinders. They have a different way of grinding up the data, and then different amounts of data coming out, but the idea is the same. And so let me talk briefly here about what makes a good hashing algorithm. Algorithm. So the one thing we're concerned about now, well, actually, one of the things we really want is that the output values are evenly distributed across their range of possible values. So, for example, for MD5, the output, as I said, was 128 bits. That means that there are 2 to the 128 possible outputs from this algorithm. And what you want is for any given data that you pour into this algorithm, you're going to get one of those 2 to the 128th, and you can't really predict ahead of time which one it's going to be. And so they're evenly distributed across the range of all those possible values. And there's not going to be not really any clumping. So in other words, if I pour in 2 pieces of data, or if I pour in bunches of data, they're not going to kind of like congeal around some common values. You want them to be, if you graphed a histogram of all 2 to the 128th possibilities, they have an equally likely chance of happening. And I know that some of you are probably going to say, well, MD5 has been debunked as insecure. Sort of. It's still useful. It's useful for talking about as far as a simple hashing algorithm. Surely, if you're doing cryptographic hashing these days, you probably won't want to use that one. And MD5 is known to have some slightly predictable output because of this problem where it's not quite as secure as it used to be. But it's still useful to talk about it. Another thing is it needs to be fast, but not too fast. So this algorithm needs to be fast, easy to compute, but not so fast that it's super easy to compute. And the idea here is if you're using this for password encryption, you want to make it so that if someone is trying to crack passwords, they can't do it really, really, really fast. But you want to make it fast enough so that your computer, your server that's trying to authenticate users isn't spending all of its time trying to compute these hashes. So I'll talk about that here in just a moment. So one of the problems with MD5 is that it's gotten to the point where it's too fast these days. The computers can grind through these things really, really fast, so you want to switch to a different one. But again, I'm kind of talking about what are the concepts behind these hashing algorithms, not necessarily getting bogged down in the details about what is and isn't secure these days. Okay, so what I want to do is show you some examples of how to compute these hashes. Now, you can do it programmatically in a programming language. You can do it from the command line. I'm going to briefly do it here in Python and show you how that's done. So let me switch screens. Here we go. I've got Python up and running here. And so there's a built-in MD5 hashing algorithm. You just say from hashlib import MD5. And then you can say MD5. And then you pass it a byte string containing the data that you want to hash. You could also pass it something like a file, but we're just going to do strings here. So if I pass in hello, what I get back is this thing called a hash object. So it's basically an object representing the hash. It's not that useful. So what we want to do is take that output and turn it into something we can see, which we do by invoking the hex digest function. And there we go. So what we got out of this is a string of hexadecimal digits. This is a 128-bit value. There's 32 hex digits there. Each one of them is 4 bits. So multiply that out, and you get 128 bits. Keep in mind that MD5's output is not, it's a number. It's a 128-bit number. It's usually represented in hex, but the hex is not itself the output. It's a number. We're just viewing it in hexadecimal. Okay, we could convert this thing to decimal, and it would be the same number, just in base 10 instead of base 16. Let's try a different string. Let's do like help. And the idea here is that by changing the O to a P, I'm essentially just, not only am I changing just one letter, I'm changing what I hope is just 1 bit. I'm incrementing the letter by 1, so I'm going up from O to P. But the point here is that you get an output that's completely different, right? It bears no resemblance to the one before that. And it doesn't matter how much text I type in. Okay, I can type in a whole lot of text, including symbols, spaces. Okay, so no matter how much text you put in, you always get 128 bits out. You could even put in a single character. Like the letter A. And that's the MD5 hash of the letter A. Now, there are other algorithms from hashlib import, let's say SHA-256. And if I do the same string again and get the hexadecimal representation, all we get is a 256-bit number out represented in hex here. So it's just a longer, it's an algorithm produces a longer output, but the idea is still the same. You still do the coffee grinder thing, you still pull out a little bit of it, and that's what you get. And then we got, let's see, whoops. Let's try 512, and we'll hash, whoops, that's the wrong one. Okay, so this algorithm just produces a longer output. It's a lot slower to compute, although it looked almost instantaneous on my screen here. The computer's actually doing a lot more work to produce that value. It's essentially, I'm looking down my coffee grinder here, it's essentially grinding it up in a different way, and my scoop that I'm pulling out is bigger. All right, so let's see, what do I want to do from here? So I've shown you the various, oh, let me do this. Let me switch over to a different window, this one here. And I've got a file here. This is the complete works of Shakespeare. And let's take a look at it. Well, let's look at some stats about it. So this file here is 124,000 lines long, and it's about looks like about 5.5 megabytes. And if I look at it, get past all the first stuff, you can see it starts out with the sonnet, then it goes into the plays. So it's everything that Shakespeare wrote. It's a long, long document. And if I compute the MD5 of this is the value that I get. And then let's go to like line 70,000. And I'm going to change one single value here. So let's make this A. Let's change that to a B. And then get a hash of that. And again, you can see I changed one letter in that whole thing, and the hash output value is completely different. And this is what you want, right? So the idea here is that if I was sending this document to you, and I wanted to ensure that it got to you uncorrupted, what I would do is I would compute a hash of it. I would use one of the hashing algorithms, and that I would send the document to you along with the hash value. You would receive that document. You would compute the hash value yourself on the document using the same algorithm, and then compare the two values. And if you got the same value out that I did, then you could be pretty confident that the file hasn't been changed. And I can't say, you can't say it for sure, but you can be pretty confident. And the reason why you can only be pretty confident is because, remember, MD5 or any one of these algorithms is producing a fixed size output, 128 bits, 256 bits, whatever. I said that the complete works of Shakespeare is 5.5 megabytes, so if you multiply that by 8, you get about, let's say it's 50 million bits, more or less. So I poured into this algorithm 50 million bits, and I got out 128. What happened to the other 49,999,000 of them? Well, essentially, if you use the coffee grinder analogy, they were lost, they're gone, they're just thrown away. I remember I dipped out that spoonful and I threw the rest away. So that means that, well, it means a couple of things. One is, it means that there's potentially many documents out there, many other documents that hash to the same value. right? So it's possible that I could pour in a different set of coffee beans, turn that grinder on, dip out my spoonful, and I get the same thing that I got with some other data. Okay? There's a really small chance, though. The chance is roughly 1 in 2 to the 128th. So that's a really big number. In fact, we can calculate what that number is. So it is 2 to the 128th. Okay, so there's a 1 in that number's chance that you can come across another document that hashes to the same value. It's a really small chance. If you want to be even more sure, use one of the other algorithms, like the 256 or the 512-bit one. So that greatly diminishes the chance that you can come across another document that hashes the same value. But really, what this is intended to catch is small transmission errors, like most likely 1 or 2 characters got changed along the way, just because cosmic rays came and flipped some bits, or data just got lost somewhere. Okay, that's the most likely thing to happen. It's not likely that the entire document got changed and happens to hash the same value. So what this hash allows you to do is be pretty confident that the document hasn't changed. So this is the same way that websites work. So when you register for an account on a website, you sign up with a username and a password. And if the website is doing the correct job, they're going to take the password that you entered on the web form, and they're going to hash it, and they're going to store that hash, and they're going to throw the original password away. So password authentication. I'm not concerned about the usernames at this point. So when you sign up, you're going to enter in a password. And then that's going to go through a hash. And then you're going to get an output value. And then you're going to store that, probably in a database of some sort. Okay, so that's when you sign up for the account. And then when you come back a second time, you're going to enter the password again. The website is going to hash it. An output's going to come out. And then what they're going to do is they're going to take that hash value and they're going to compare it against what they have stored in the database. And if those two come out to be the same, then they can be fairly sure that you typed in the correct password. They can't be 100% sure. Again, there's a 1 in 2 to the 128th chance that you typed in a password that happened to hash to the same value, but that's extremely unlikely. So unlikely that it's essentially zero chance that could happen. So how do hackers actually go about cracking passwords? So here's the important thing, is that because the output values are evenly distributed across the output range, it's impossible to reverse a hash. Okay, go with me here. It's impossible to reverse a hash. In other words, because I poured in all of those coffee beans and I ground the thing up, and then I pulled out just a teaspoonful and I threw the rest away, there's no way for me to take that teaspoonful and reconstruct the original beans. It's totally impossible because data's been lost. A lot of data's been lost. You could maybe, this is really stretching the analogy, you could maybe reconstruct something sort of similar to the original beans, but there'd be lots of holes in it. But essentially the chances are 0 that you can actually reverse a hash. And that's the whole idea, is that by storing just a hash of the password, we're not storing the original password at all. There's no way to recover the original password. So how do hackers actually go about cracking passwords? And this is a timely kind of thing happening because it's middle of October. You may have heard in the news that companies like Yahoo recently had a whole bunch of their accounts compromised, and it turns out it's maybe as few as 500 million accounts and as many as 1 billion accounts. And so hackers have gotten a hold of usernames and the hashes of their passwords and are working, probably to this day, on trying to crack as many of those as they can. If they can recover those passwords, that's useful information because it turns out humans are not very good at picking passwords, and they tend to use the same passwords on different sites. And so if they can crack a password on a Yahoo site, they can probably also use that same password and username on a different site and get in. So that's the real risk here, and this is probably, I think I heard this is the largest breach of its kind in history, with almost 1 billion accounts being compromised. Which means, now, you know, you log on to Yahoo, and you know Yahoo is probably full of a lot of fake accounts. So how many of those are actually real active accounts? Who knows? But they're working on cracking those things. So how do passwords actually get cracked? Well, since you can't reverse them, the most straightforward way to crack passwords is just what's called a brute force algorithm. Brute force. You're essentially going to try every possible password, and you will get it. You'll do it this way. So start with A, and then B, C, D, go all the way to Z, and once you exhaust all of those, do AA, AB, AC, AD, AE, all the way to ZZ, and then once you exhaust all of those, do AAA, AAB, AAC, and do that for pretty much every password length possible. Do 4 characters, 5 characters, 6 characters, 7 characters, 8 characters, 9 characters, 10 characters. You will eventually crack all the passwords that way. Now, that's assuming the passwords are lowercase. If the website requires uppercase and lowercase, well, then you've got more combinations to try. If it requires uppercase, lowercase, and at least some numbers, then you've got some more combinations to try. Maybe they throw in some symbols, you've got more combinations to try. But the point is, you can eventually work through all of them and crack all the passwords. Now, how long is that going to take? Well, we could get a rough approximation of how long that'll take. Let's say the website requires us to use uppercase, lowercase, and digits in our passwords. And let's just say for now that it's any mix of those. So it could be all digits, could be all letters and numbers, all letters, but we'll just work with that. So that means there are 26 letters, 26 uppercase letters, and 10 digits for a total of 62 characters you could use in the password. And then let's say the website also requires that the passwords be between 8 and 10 characters long. Okay, so we go 62 to the 8th. That's how many 8-character passwords we can have. And then 62 to the 9th. That's how many 9-character passwords we can have. And 62 to the 10th. That's how many 10-character passwords we can have. And if we add those together, that's the total number of passwords we've got to do. That's a big number. Okay, let's, I'm going to copy that number. Let's say we can do, I don't know, let's say we can do 5,000 of those per second. And we work at it 24/7, so that's the number of hours. Yeah, number of hours, number of days. So that's the number of days it would take us to work through all of those. That is, what is that number? I'm counting 1.9, almost 2 billion. Almost 2 billion days to crack all those. So let's go a little bit further. That's the number of years. So only 5.4 million years to work through all of those passwords. Only. Well, okay, so you say like, well, maybe 5,000 per second is not really a realistic number. Maybe I've got a whole bunch of computers and we can do 1 million per second. Okay, and then we'll divide by 365 again. Okay, so only 27,000 years to work through all of those. That's still a long time. But you know what? These days, computers can probably do more than 1 million per second. Let's say they can do 1 billion per second. Okay, 27 years. Okay, that's still a long time. But now we're getting into, well, all I need now is like 27 computers, and I can do it in 1 year. So now we're getting into kind of the realm of realistic. And I'd say 1 billion here is actually not unrealistic. I could probably boost this number up to 4 billion, and now we're just looking at 6 years. So as a website operator, you should be concerned about this. you should probably think maybe 10 characters is not enough. What happens if we go to 11 characters? So let's just add on 62 to the 11th. Okay, so 8 through 11 characters. All right, so that number is a bit bigger. Let's go ahead and divide it by 4 billion. And then divide that by the number of seconds in an hour, and then divide by the number of hours, and then divide by the number of years. So we're now down to 419 years. So this should point out to you, oh, actually, let me do one comparison here. Let's say I allow uppercase, lowercase, and I throw in a couple of symbols. So let's say I require a couple of symbols. So let's go to 64 characters. And you compare these numbers, and you see that although they're big, they're pretty close to each other. See that? The magnitude of the number hasn't changed much. I went from 5 on the first digit to 7 on the first digit, so it didn't change a whole lot. So as a website operator, and as you as a user should be concerned about, or should keep in mind, is that it's better to go for longer passwords rather than more characters. I added 2 characters to the mix, and I only went up in complexity by a little bit. But I add 1 more character to it, and the difference is between this one and this one. And you can see I added on 2 digits, so I made it, well, I can tell you, I made it 62 times more complicated. So what used to take 419 years, what used to take 6 years is now going to take 300 years. More or less, maybe 400 years. Okay, so it's better to make longer passwords than to make more characters. And then, actually, the worst thing a website can, almost the worst, no, I shouldn't say the worst thing. You run across these websites that say, like, hey, passwords must be 8 to 10 characters or more, and include a mix of letters and numbers, and include at least 1 symbol. And what they're essentially doing is they're putting more and more restrictions on the password. They're saying it has to contain at least these number of characters, it has to contain at least one of these characters, and at least one of these other kinds of characters. And that's actually reducing the number of passwords that you can possibly use. I mean, I know the idea is to get users thinking about adding more characters or adding the different kinds of characters to their passwords, but it's really actually better to allow them to make longer passwords. That's really what you want to allow them to do, even if they're using fewer characters. So even if they use just letters and spaces or dashes or something like that, so even if they're using only, let's say, 36 possible letters, if you allow them to make 20 character passwords out of that, you're in a much better shape than requiring them to put lots of weird symbols in their passwords, which they'll never remember, so they end up writing it on a note and sticking it to their computer. So that's what you as a user should do. And actually, I would recommend, if you're not using a password manager these days, you should get one. Password managers, when you sign into a website, they can automatically generate a completely random password that obeys all the rules of the website. So it's got symbols and letters and numbers in it, and you can make it as long as you want, and it's all just protected by your mastered password, which hopefully should be a fairly long one. And then it remembers all the passwords for you. And then you can also guarantee that every password on every website is unique, which is going to save you if somebody breaks into one website. If they crack your password, it's not going to work on any other website. But what I want to do, show you tonight, is how to crack passwords, given that you can't reverse them. And I know some of you in the chat are probably going to say, what about salting this thing? I don't want to get into salting for now. I just want to show you the concept of how to crack these passwords. And so, given the fact that humans are terrible at choosing passwords, the best way to crack a lot of passwords in a short amount of time is to use common passwords, commonly known passwords. And so there's this file that you can download called rocku.txt. If you just Google for it, you'll come across a website that's distributing the file. And it's a good thing to have. I'll show you the first few lines of the file. There's 14 and something million passwords in this file, and they're ranked from the most popular up at the top down to the least popular at the bottom. The file's a little bit old. It's from 2009, but the ranking of the most common passwords essentially hasn't changed in 7 years. So you can see here the most common password as of 2009 is 1234565 followed in second place by 1, 2, 3, 4, 5, and in third place 1, 2, 3, 4, 5, 6, 7, 8, 9. Fourth place is finally password as one of the most common passwords. This one right here, the one that's in 8th place, Rocky, is probably why the file has its name. But you can see that people tend to just choose numbers as passwords. And I'm not going to scroll through this file, in part because it turns out humans not only choose common passwords, they also choose ones that sort of can't be shown on public television or YouTube. So I'm not going to show you much more of this file. But needless to say, there's 14+ million passwords in here. You should probably download this file and search through it for passwords that you use. And if one of your passwords is in this file, you should change it immediately, because this is the first passwords that password crackers try when they're trying to crack passwords. So there's a question of what password manager to use. Well, it actually depends upon what operating system you use. I'm using the Mac here, and so I use a password manager called 1Password. That's the number 1 followed by password. The nice thing about it is that there's plugins for all the major browsers, Safari, Firefox, Chrome, and then it also works on my iPad and tablet, and they sync across all the devices. So using my iCloud storage, which is protected by my own password, it syncs between the devices, and so I get the same password manager on all of my devices. And they also, as of I think iOS 9 or 10, 1Password can also integrate in with, I think, with the keyboard or with any application. So any application that asks for a password that's aware of 1Password pops up a little symbol that says, click here to pull in your password from 1Password. So it's a nice password manager. I don't have any explicit recommendations for other ones. I know there's like LastPass for Windows and some others. However, I was a little shocked to discover when I went and searched for RockU the other day. I went to that website that distributes that file. There was another file there that said LastPass. So apparently someone had broken into LastPass and gotten a whole bunch of passwords out of that one. So I've heard people use that one, but I don't know whether to recommend it, just because it appears to have been cracked at some point in the past. So that's the one I use, is 1Password. So let's crack some passwords here. So the idea is loop through this file. So actually, let me back up. You need some passwords to crack. And so I'm sure if you went out and Googled around a little bit, you'd come across some websites where people have taken, I guess what they do is they've stolen password files from websites. I don't know where they get them. Honestly, I don't know where they get them. And then they post a list of all of the hashes that they found, and then you can just go to home on it. Usually on these files they don't tell you where they got it from, so I don't feel too bad about cracking these passwords, because I have no idea whose passwords they are. And so I grabbed one. Here's what it looks like. It's just MD5 hashes. I don't know where they came from. Here's another one. Okay. So remember, it's for all practical purposes impossible to reverse these things. So even though this is a hash, an MD5 hash, I could do a brute force algorithm on it, but that would take a long time. What I want to do is try every password in that RockU file against these hashes and see which ones happen to match. So as I said, what we want to do is take every single one of these 14 million passwords, hash them, and then match them against that file and see if any of them match. If we got a match, we'll print out the hash along with the matching password, and then we know that we've cracked that one. And we just roll to the next one. And so it means that if we've got, let's see, how many do we have here? 2,130. So 2,130 times 14 million, let's say it is. So that's only that number of combinations to try. It's really not that many. You could easily write a program to do this. It's just 2 nested loops, one looping through the RockU file, one looping through the file that has your unknown hashes in it, and just start hashing the RockU file and match them up and see if you've got any matches. You only have to do that this number of times. What is that number? Million. 29 billion times. Oh, you know, take a few minutes for your computer to do. Really, it would just probably take a few minutes for it to do. But these days, hackers, and there's white hat hackers and there's black hat hackers. White hat hackers are doing it for good, ostensibly. They use the same tools as the black hats, it's just their goals are different. The white hat hackers are doing it to try to improve security, and the black hats are trying to do it for their own purposes. And so the software that a lot of hackers use is called hashcat. Here it is, you get it from hashcat.net, and it's available for Windows and Mac and Linux. And everyone these days has like a dual core or quad core processor, and so if you've got a couple of cores that you could use, it'll use them. But where it really gets a speed up is if you happen to have a video card in your computer, and it doesn't really matter whether you've got an expensive NVIDIA or AMD graphics card, or if you've got just one that's built into the processor. The nice thing about video cards is they have multiple processors that you can use, and they work in parallel. Because when you're cracking passwords, you can easily parallelize this problem. You can, so if your graphics processor, let's say, has 500 graphics card has 500 processors on it, you can get all of them working simultaneously on this problem. You just give them all the same algorithm, the same hashing algorithm, and you just feed them different passwords, and they go through and do their job. So on my computer here, I happen to have a NVIDIA GTX 980, which as of a couple months ago was one of the faster cards that you can get on the market. And I think, if I recall right, it has about 1,200 processors on it, which means that's how many processors it can work on this problem simultaneously. So what I'm going to do is I'm going to say hashcat mode 0. Mode 0 means I'm trying to crack MD5 hashes. Here's the file that I want to do, and then I'll go against this dictionary, the RockU dictionary, and then it will go to work. Okay, so in just in less than a second, less than 1 second, it found, how many was that? 11 out of the 2,130. You can see that number right here. So these are passwords that directly appeared in the RockU file. So, you know, it found Maria 123456 in there, and there was a match against this hash, and so it prints it out. But that's not so good. That's less than 1% of them. So, you know, the common way to pick a password when you can't think of anything else is to take a word that you remember and then do something to it, like stick a number on the end, or change one of the letters to a symbol, or capitalize one of the letters, or stick two words together. So there's this file which looks like gobbledygook to you and me. Okay, but each one of these is a transformation rule. I don't know exactly what this means. I haven't read up on what all these codes mean, but it does things like take a word and repeat one of the letters, or take a word and put a number on the end, take a word and capitalize it, take two words, put it together. So it does all these transformation rules, and there's 30,000 of them. Imagine that, 30,000. So we're going to take that 14 million words, and we're going to each one of them, we're going to apply one of 30,000 transformation rules, and then compare that against the 2,000 hashes I've got. Okay, that is, I think, a fairly big number. So if we take the 14 million and we multiply that by the 30,000 rules, and we multiply that by the hash that we're trying to crack, that's the number of calculations we have to do. I don't know what that number is. That's a huge number. It's in the trillions. Okay, but we can work through them. So let's run hashcat again. But let's say not only are we going to use this dictionary, we're also going to apply these rules to them. So that's the -R option to this. Okay, and here we go. Now, I apologize in advance if something scrolls by that offends you, but that's likely to happen here. But you can see how fast this is going. Okay, and I can hit S here for status. And let me pause it for a sec. Okay, so take a look at this here. 2277 mH per S. So this is 2,277 million hashes per second. So it's doing 2.2 billion hashes per second. Remember that number I gave you about 15 minutes ago where I said 4 billion was not too unrealistic? It's because of this. All right, let me point in the right direction. That's because of this. All right, 2.27 billion hashes per second. And that's with a graphics card that's about 2 years old. So the latest one that came out, the GTX 1080 or something like that, is the latest one you want to use. I hear it's about twice as fast. So it can probably do about 4 billion hashes per second. And that's assuming you have one in your computer. If you do this professionally, you're going to want to buy a computer that has as many of those slots in there as you can fit, and then put as many of those cards in there as you can. Let's say you put in 4 of those cards, and now you're doing about 12 billion of these per second. So you can crunch through this file pretty darn quickly. Let's let this thing keep going. And what we can also, let me pause it for a sec. What we can also see is that, remember that number I came up with? There's that number, more or less. There's that number. We are already 16% of the way done. Actually, I'm going to put it out of its misery here. All right. I mean, it will only take like a couple minutes for this thing to be completely done. Let's try it on my other file. What was this one here? Oh, let's try it without the rules. See how many you can do just right off the bat. None. Okay, there were no hashes in that entire file that matched any of the passwords in the Rocky file. But let's try it with the rules. Oh, wow, that's fast. Okay, so applying these transformation rules has now allowed it to crack quite a few of the passwords. And let's see, status here, 5% done. 8% done. 13%. 20%. So we've only been at this for less than a minute, and we're already about 1/5 of the way done. About a quarter of the way done now. The computer that's doing this is just on the other side of the room, and I can start to hear the fan ramping up. You can see the very last line of the status tells you how hot the GPU is getting. 35% done. %43 done. Yeah, I don't want to bore you with all the output here, but basically, when this thing gets done, it will have found approximately, oh, actually, it's already up to half of them, and we're only halfway done. So I'm guessing we're probably going to crack 60, 70, 80% of the passwords by the time we're done. Okay, it may not find all of them. There's probably some that are just too complicated to be discoverable using the rule set that we have, but you'll get a lot of them. And that's significant because it means that a hacker who is trying to break into a website at least has access to, wherever this came from, 900 accounts so far, 900 accounts. And so can get in that way. And maybe one of those has elevated privileges, maybe, so you just try them. All right, so hashcat is, if you're interested in doing password cracking, hashcat is the tool for you. And it not only understands algorithm. Let me see if I can zoom in here a bit. It not only understands algorithms like MD5, it understands how to do SHA 256, 384, 512. Plus it knows how to use combinations of these. So a common thing for some websites to do is, let's say, to take a password, run it through MD5, and then run that through one of the SHAs. And maybe do that multiple times. Some websites will take a password and run it through a hashing algorithm, let's say 100 times or 200 times. And so the trick is then, if you're trying to crack these passwords, is to know how many times to run it through again to try them out. And if you can't guess the right number, you'll never be able to crack the passwords. But there's ones in here for cracking Windows passwords, Mac passwords, Cisco passwords, Oracle passwords. Here's LastPass right there. See? KeyPass. So this is a tool that you probably want to be using if you're interested at all in cracking passwords. Okay, so let's see. Let me switch over to the screen here. So we were talking earlier about properties of good hashing algorithms. And so one of them is called pre-image resistance. And what that means is that, let's see, given a hash, let's call it H, it's difficult to find the message, let's call it M, that hashes to it. That is, the hash of the message is equal to H. Okay, so pre-image resistance says, given a hash, it's hard to find the original message that hashed to that given hash. And that's exactly what we were trying to do with password cracking. And by hard, I mean, by hard, I mean, like, at worst, you would have to do a brute force algorithm. At worst, you would have to try every single combination to crack that thing. And that's what it means by hard, because it would take years and years and years, or millennia, to pull that off. Okay, so that's what pre-image resistance is. It's hard to basically reverse it. And then another one is called second pre-image. And what that means is, given a message, we'll call it M1, it is difficult to find another message, we'll call that M2, that hash to the same values. Okay, so if I give you a piece of data, let's say the complete works of Shakespeare, or a password, I'm going to say to you, find me another piece of data, like another password or another complete works of someone else, that happens to hash to the same value. And that's really difficult to do. So if I give you one piece of data, find me another one that happens to hash to the same value. Now, those of you who are listening into the live stream, it's MD5 that actually doesn't obey this here. You can find another piece of data that happens to hash to the same value. I'll show you an example of that here in just a couple of minutes. Okay, but all the others, SHA and RIPE-MD, as far as we know, obey these two properties. And there's a third property. And this is called collision resistance. And this means it's difficult to find two messages M1 and M2 such that they hash the same value. Okay, and you may think that this one and the previous one, second preimage resistance, look really similar, right? The part that looks really similar is this part right here. These two messages hash the same value. But it turns out the second preimage resistance is the more difficult of the two. Because in this one here, in this collision resistance, all you got to do is find two messages somewhere out there that happen to hash the same value. In second preimage resistance, I give you one of the messages and you got to find the other one. Okay, that's harder to do. This one is you just got to stumble across two of them. But it's that second preimage resistance that's really important. And it's what MD5 has essentially fallen to these days, in part because computers have gotten faster. So it is possible to just kind of grind through the data and find another one that happens to hash the same value. So the way that MD5 works is that no matter how much data you pour into it, it takes that data and it chunks it up into 64-byte chunks. And then it grinds each one of them up, and then it grinds the next chunk up and grinds the next chunk up, and then all of those chunks get combined together to produce the one final output. And so that 64-byte chunking is part of the reason why MD5 has fallen to second preimage resistance. If I go to a directory I've got a directory called collisions, I have these two files here, message1 and message2, and they're different. Okay, they're both 64 bytes. There's that magic 64 bytes, but they're actually different on the inside. But if I compute the MD5 hash of both of them, you see they're the same hash. Okay, and if I dump out, oh, you can't see what I'm doing. I'm sorry, I gotta switch screens. There we go. Okay, so the backup here. So I have these two files, message1 and message2, and I computed the MD5 hash of each one, and you can see that they're the same. However, if I dump the contents out, so this command here called xxd will do a hex dump of a file. Here's all the hexadecimal data that's in it, and here's the ASCII representation of it. It's just random gobbledygook for all I know. Okay, but there's actually a couple of differences between them. If you look closely, there's a difference here, which corresponds to this character and this character. You see that? So that's different between them. And then there's another place right here and here where they are different, and that corresponds somewhere over here. So there's two places in the file where there's a difference. And essentially, I think they're basically one bit difference. Like, difference between a 0 and a 2 means not the least most significant, but the second least most significant bit has been changed from a 0 to a 1. And the same thing here. I think this is also a 1-bit difference. So all we had to do was change 2 bits in the file. And remember what I originally showed you, that if you change just 1 or 2 bits, you're supposed to get a completely different hash value. But in this case, they come out to be the same. So some people did some research on MD5, and it turns out that there is a little slight clumping of output values. And they wrote a paper and they say, like, if you take a 64-byte chunk of data and you change the bits in these few places, you're going to have to grind through millions of combinations to find the exact bits to change, but you can come across a second message that happens to hash to the same value as a first message. So if I give you this file, you can do some number crunching and find another file that happens to hash to the same value. All right, this is random data, but you go to a website where you download a program, and I can't think of a website off the top of my head to do on the spur of the moment, but you can go and download an application or a data file, and usually on these websites they'll give you a hash value. They'll say the SHA checksum of the file is, and they'll give you a string of digits. And the idea is you're supposed to download the file, run the same hashing algorithm on your downloaded file, and match it with what the website gives you. And if there's a match, then you can be sure that the file you've got matches the one that you were supposed to download. It hasn't been corrupted in any way. None of the bits have been changed. But the problem is, it's possible to come up with another file that happens to hash the same value. So I've got here two programs, hello and erase, and they hash to the same value, right? So you could go to a website and download what you think is a nice program, let's say to help out with your homework or organize your finances for you, and you run it, and it does something cool like greet you. But it turns out that what you actually downloaded is one that erases your hard drive. No, just kidding. It doesn't really do that. Okay, but you ran the hash algorithm on it, and you were positive that you got the correct file because it hashed the same value, but it turns out you actually downloaded malware. Okay, so this whole problem of the pre-image resistance is why people kind of discourage you from using MD5 these days, because of this. It's possible to find another piece of data that happens to hash the same value. It's still really difficult. This program, there's a program that makes these programs called Evil Eyes. Here it is. You can go Google for it. But the README for it says you got to do these steps. You got to write some programs. You got to combine them together, and then you have to let it crunch on the data. And it says it could take a while, like several hours or several days, to finally find the two programs that happen to hash the same value. So it takes a long time to do, but it's not really doing brute force. It's because of the research these people have done, they've essentially really condensed down the search space to find these values. And so it won't take millennia to find, but it might take a few hours to find. Okay, so that's my basic introduction to hashing. Now, the last thing I guess I wanted to show you was, and I don't have a good example of this ready to go, unfortunately. I didn't plan for this, was MD5 is a fast hash algorithm. It's many years old, and in decades past, it was, remember I said it should be fast but not too fast, so it fell into that ballpark of fast but not too fast. But the problem is these days it's too fast. I can do 2.2 billion of them per second with my 2-year-old graphics card. Imagine what I could do if I had a more recent graphics card. So MD5 has fallen out of favor also because it's just too fast. So you want to use something like SHA 512 or 1024 because it's slower. In fact, if I was to generate a whole bunch of hashes of everything in the ROCU file and then say go for it, we would find that the hashing rate falls from 2.2 billion per second to just a few hundred per second. So these hashing algorithms are not only produce longer output, but are slower to do. And that's also a good thing, because it means that someone who's potentially trying to hack passwords has more work to do, a lot more work to do. So instead of doing 2.2 billion per second, they're going to do a few hundred per second. So it's going to take them longer to crunch through all of that data. But they're not so slow that a web server that's legitimately trying to authenticate users isn't spending all of its time running these hashing algorithms. It's got enough processor power left over to be able to authenticate users quickly and get them on their way. So I think that's basically what I had. More or less a review of what I did over the last week in my class. I know this is not the typical type of topic that they talk about in a discrete structures or a discrete math class, but I think it's really interesting because it brings together a lot of the stuff that we have been talking about, like modulo, arithmetic, representation of data in binary, and those sorts of things. And a lot of you get a real kick out of seeing how passwords get cracked in the real world. So I think what I'm going to do is I'm basically going to wrap it up. There's several people in the chat, so if they've got any questions, they can post those questions and then I'll answer them as best I can. So I'll wait. What I'll do is I'll say goodbye for now, and then I'll wait about 30 seconds or so, and if I see some questions, I'll answer them then. So goodbye. I'll see you in class or see you online in a couple of weeks, and have a good evening. Bye-bye. All right, so this is where I wait because there's about a 30-second delay between when I say something on YouTube and when you see it on the screen. So that's why I got to wait a bit. So we have a question here. Please do a video on socket programming in C. You know what? I did some of those videos a couple years ago. Look through my playlists or my channel. You'll have to scroll back a couple of years, but I do have some videos on doing socket programming in C. Actually, I did it, I think, mostly from the server end, because what I was doing at the time was I was designing a program that my students would write the client for. So I was writing the server, they'd write the client. And so I wrote one in C. It's a chat server, I think. Well, thank you for saying that your lectures are my favorite. Although, I guess they're not really lectures, because I'm just blabbing off the top of my head. Oh, goodbye, Virya. See you later. Well, I don't see any other questions, so I'm going to end this now. And I hope all of you have a good evening, and I'll see you later.